With this video, we start a new chapter on chemical equilibrium. Until now, we have studied equilibrium in two circumstances. One of them was physical equilibrium, that was chapter 4, and then we have equilibrium in non-electrolyte solutions, and that was chapter 5. Alright, so just to put into context what this new chapter is going to be with respect to those other two chapters, that is that in chapter 4, okay, we were simply studying physical equilibrium, okay, which was essentially used a pure substance, and you were studying the equilibrium between the various phases of this substance. For example, here you would have perhaps liquid water, and then we studied the equilibrium between the liquid phase of water and the solid phase of water. Okay, that was chapter 4, and we learned a variety of things about that physical equilibrium. Now in chapter 5, the thermodynamics of non-electrolyte solutions, what we actually did is say how the properties of a solution, how the stability of a solution gets altered when you add here a solute called B. Okay, now an important aspect of these non-electrolyte solutions is that A and B did not react. B only changed the freezing point, the boiling point, perhaps the osmotic pressure of the solution. Okay, now what we study now in our chapter, new chapter, chemical equilibrium, is what happens when you actually have now two solutions, A and B, but they can react. Okay, so maybe A and B are two reagents of the same reaction, or maybe A turns into B and then B might react to turn into A. Okay, that's the type of phenomenon that we're going to be interested in this chapter. Okay, it turns out that life works really hard to try to avoid situations of equilibrium. For example, when you think about a cell, okay, and you think about the number of ions inside and outside the cell, we know very well that that concentration of maybe sodium ions or potassium ions is quite different from the inside and the outside of the cell. Okay, as a matter of fact, if you ever reach chemical equilibrium in which the concentrations inside and outside are the same, then that cell would not be viable, it would die. Okay, so again, it looks like by having here ion pumps and structures like that, life is working really hard to avoid situations of a chemical equilibrium, and that happens to be the case, right? So it's quite important to understand what the point of chemical equilibrium is, as this is a pervasive concept in chemistry, biochemistry, and the life sciences in general. Okay, so for chemical reactions, we already have a way to calculate when you have reached chemical equilibrium. For example, one of the things that we could do here is to try to calculate what the reaction Gibbs energy would be for this particular reaction A to produce B. And what we actually know is that if you're working under constant temperature and pressure, if the calculation of this reaction Gibbs energy happens to be positive, then the reaction will not be spontaneous. If it happens to be negative, then the reaction will be spontaneous, and we might be able to extract some energy as work from that process. And then the point of equilibrium, which is the title of this chapter, would happen when you have that the Gibbs energy is equal to 0. Now, something that we actually have completely ignored in our discussion of the reaction Gibbs energy until now is that when we calculate these numbers, okay, by utilizing both the enthalpy and the entropy, okay, notice that the calculation of the enthalpy of a reaction and the entropy of a reaction until now has been done with reactions that we called or with values that we call standard. Okay, that means that our calculations have been limited to something that is called the standard state. And what is the standard state? Well, the standard state, from the values in the tables, were those in which the pressure was equal to 1 bar. Okay, so only when you have a pressure of equal to 1 bar, you actually can use the values that we have calculated. But you can see how this is clearly very limiting. Okay, for example, let's go to the atmosphere and try to calculate what the reaction Gibbs energy would be for the reaction between nitrogen and oxygen, the two most abundant species in the atmosphere, to generate NO. Okay, so calculation of the reaction Gibbs energy for that process would be trivial. You simply go to the tables and then get the enthalpies of formation, get the molar entropies, okay, and those will be standard and at 288 Kelvin, and then you will calculate the standard reaction Gibbs energy. But again, that implies that every substance is at 1 bar of pressure, and that's not what happens in the atmosphere, right? The pressure of nitrogen is not 1 bar in the atmosphere; it's about 0.771 or so, 78. The pressure of oxygen is not 1 bar; it's going to be much less than that. It's going to be about 0.20 bar or so. So what that means is that we actually, even though we can calculate this number, that would not be a faithful representation of what really happens in the atmosphere, okay, when we think about this reaction. All right, so you can clearly see how our calculations until now are fairly limited. We actually, again, would not be able to know what happens under actual concentrations. Now, when we go to cellular processes, this is even more important. Think now about the metabolism of glucose that necessitates oxygen as a reagent and generates CO2 as a gas. We have calculated the value for the delta Rg, again for the aerobic combustion of glucose. That number happened to be about minus 2880 kilojoules per mole. But again, that was at the standard state, meaning that the pressure of oxygen and the pressure of CO2 would be 1 bar in that process. Clearly, that's not the concentrations, the partial pressures of oxygen and CO2 in our cells, where they're going to be much, much less than that. Right? So what we're going to be doing in the next few videos is trying to understand how we can actually calculate delta Rg, not for the standard state, which we already know how to calculate, but for any state that we're interested in, any set of concentrations that we might be interested in, like those inside a cell or maybe those in the atmosphere.